Hi, welcome to Theoretically Podcasting. This is Vasu Sham, and today I wanted to do a little walkthrough of a paper that caught my attention, namely this one, titled The Weiss Variation of the Gravitational Action, by Justin Feng and Richard Matzner. It's from a little while ago, but I thought that the points they make, some of the lessons contained in it are astute and interesting. So the basic idea is that they propose having a free endpoint variation of the action, which is basically how it would manifest if we were talking about mechanical system. And in the case of gravity, they propose having essentially the ability to sort of vary the boundary embedding, as it were. And I mean, this sort of clarified things for me. I thought it was a very neat trick. So let's just go through the mechanical example first. So let's just start with mechanics. And, we all know the drill. We'll start by defining variations as follows. Take eta here to be infinitesimal. But in addition to doing just that, what we do is we also sort of vary the endpoints over which we're sort of doing the integral of the Lagrangian and defining the action. So now the variation isn't just a variation involving the argument of the Lagrangian, but also the endpoints up here and down here. So what does that do? Well, I mean, first it gives us the equations of motion as we'd expect. But in addition to that, there's also going to be variations involving the endpoints. So we have the original Lagrangian, right? We take eta to be infinitesimal, so we have what will give us eventually the equations of motion, and then we have these two terms, which go from T1 to T1 plus epsilon tau 1, and T2 to T2 plus epsilon tau 2. And the net effect of this is that in addition to our standard Euler-Lagrange term, we're going to have the following on the boundary, as it were, because this is just an integral over time in the mechanical example. And the boundary is just the evaluation of the integrand at the endpoints. And notice that here, in addition to having this eta I with the epsilon, we also have L delta t, right? And so delta t is this quantity that satisfies the following property. When you take it, evaluate it at T1, it's epsilon tau 1. When you take it and evaluate it at T2, it is epsilon tau 2. Great. So now we have a way, essentially, of being able to vary the endpoints. Okay. And so they say that it is also convenient to rewrite the boundary term in terms of the total displacement along the endpoint. So basically, in addition to defining delta t, we'll define delta q1 and delta q2, right? So here, notice that we have a very standard looking term that comes from doing the integration by parts. But in addition to this term, well, what we're going to do is we're also going to extract delta q1 and delta q2. So what are those? So delta q1 is basically q prime at t prime 1 minus q at t1, right? So this is all happening at the initial time, and then delta q2 is happening at the sort of final time. And when we do that, right, so what do we get? Basically, the result of the variation involves eta, but since we're also varying the argument t, it involves q dot times tau. And now based on whether we're evaluating at T1 or T2, we're going to have tau 1 or tau 2 in the arguments. Perfect. So that gives us, in the end, that the variation of the action doesn't just contain the Euler-Lagrange term and this L delta t term, but you also get an extra p q dot and swap eta I for delta q, right? So what's happening is that you're inverting the relation here between delta q and eta. What's the upshot? Well, the upshot is that you discover the Hamiltonian. You get the symplectic form in terms of this delta quantity, but you also discover the Hamiltonian without meaning to do the Legendre transform. So this is completely consistent with the things we know. And no, it's a very cute way of reorganizing the variational principle when we're talking about mechanics. But we'll see that this fact of the Hamiltonian being the coefficient of delta t here has a parallel in the case of general relativity, which is a rather interesting one and ties back to things we know from holographic renormalization. So how does this carry over into field theory is the first natural question. And the answer is that in addition to considering the usual variation of the field, its derivatives, and so forth, we also take into account the sort of coordinate field. So basically what we're going to do is look at what happens when we actually vary the sort of embedding of the boundary. And we'll see basically how that manifests. So it's easier to just go through the mechanics of the variation rather than dwell on the definitions of the various symbols, is what I find. So if we proceed, then the procedure is not all that different from what we saw in the mechanical case, except what we're going to do is we're actually going to vary this term x mu. So we're going to get an extra term on the boundary, which is the evaluation of the boundary integral of the Lagrangian delta x mu, right? So well, what's going on there? So basically this quantity x mu is the embedding of the boundary in the bulk, right? So that yi, so it's a function of yi, the coordinates on the boundary, and the variation that we're doing here, it's basically to see that, okay, the analog of the free endpoint variation, the variation of the integration bounds of the Lagrangian, will correspond to varying this embedding in the context of field theory, right? That's a sort of covariantization of the process of just varying the endpoints, or sort of allowing for the variation of the endpoints. And what it does is that it just gives us a term on the boundary that evaluates to the Lagrangian delta x mu dotted into the surface element of the boundary. Okay, so then what do we get? Well, in much the same way as the mechanical example went, we're going to get the following. We have first S, we have the result of doing the variation before we integrate by parts. And then we have L, as I said before. And what we'll do is sort of perform again the sort of variation with, of the boundary fields that'll later help us reorganize everything. So that means that we're going to have basically the following breakup of terms on the boundary. Okay. Great. So then we do the usual integration by parts, and then we sort of absorb this thing on the boundary too. So in addition to L delta x, we're going to have this additional term. Great. And we get the standard Euler-Lagrange equations. But now we're going to do the analog of what happened with going from just this standard structure here to one that doesn't involve this variation delta, little delta, but the one that involves the big delta. That is the one that takes into account the variation of the boundary embedding as well. And basically, we want to rewrite what we're calling little delta phi here in terms of the big delta. So what do we mean by that? Basically mean by big delta that we're going to take phi plus delta phi at the varied boundary, that is partial w prime, minus phi at the original boundary. Okay, and just like before, in addition to being delta phi, that also includes the following term, which is the derivative of phi dotted with delta x, right? Cool. So in so doing, what we get is the following structure, which, again, much like how it worked in the mechanics case, reveals to us the Hamiltonian, but really what we're getting is this tensorial structure here, because you see we're varying the embedding fields. Okay, so in their definitions, basically you have this P mu A, which is like the momentum, except that they call it the Pauli momentum because it doesn't just involve the derivative of Lagrangian with respect to the field velocity, but just the general derivative of the field along any direction. And you see that it has this tensorial structure, which when you take the derivatives, the indices to be the zero indices, gives you back the canonical Hamiltonian. And so to basically get this canonical Hamiltonian, well, what would you have to do? You would have to basically take x, delta x to be in a direction that's sort of time-like, essentially, and look at the zero component of that. So that's kind of basically telling you the familiar thing that the Hamiltonian controls what happens when you sort of move a constant time surface up or down. And here they just go over how you would rederive the familiar notions and what the, what the idea is. So basically you take delta x, as I said before, to be a variation in the direction of, time, provided that you set up the boundary to be basically the union of these two surfaces, sigma t1 and sigma t2. And it just tells you that the Hamiltonian tells you what happens when you move in that direction. And so that's all that happens in field theory. So the upshot of this variation is that you're not just capturing the equations of motion, you're also getting your definition of the Hamiltonian for free. And now what's amusing is that their analysis of the gravity case indeed recovers what we know to be the gravitational Hamiltonian, but it also tells us something interesting about the boundary terms. So they tell a slightly longer story here, but basically, oh, sorry about that. Basically, the idea is that in addition to having the variation of the gravitational action, they consider the variation of various area functionals, as they call them. So the area functionals they're referring to are just different sort of like actions on involving like world volumes and they could be of any codimension in principle, but mostly they look at codimension 1. So I'll just jump to an appendix which deals with the first and second variation of what they call the area functional, the area formula. Okay, so this shouldn't be too surprising, but okay, they start by recounting some definitions, which is of the space-time volume form, and what happens when you take the lead derivative of the volume form with respect to some vector field. Okay, so first they say, okay, this is the identity that you get. And now notice two things, right? First, if the vector field with which we're taking the lead derivative is the normal to some hypersurface, then because of the relation between the divergence of the normal and the trace of the extrinsic curvature, you get the following relation, all right? So you get the sense that like the trace of the extrinsic curvature is something like a logarithmic rate of change of the volume of some, of some space. But more importantly, you can actually see it as the fractional rate of change of the surface element itself. Okay, so what is the surface element? Well, the surface element is just the interior derivative of the volume form, right? So the interior derivative of the volume form with respect to the normal gives you the volume element of that codimension 1 surface. Great. Nice. And then they say, let's take the lead derivative of that with respect to n. Okay, so just expand, use the various identities you already know, and see that actually the lead derivative of this surface element is the trace of the extrinsic curvature times that surface element. And that will basically lead to the following very interesting results. So they say, at some point, you're going to have to consider if you're going to really just do the variation of a gravitational action with sort of displacement of the boundary, then we're going to have to consider this delta variation of d big sigma, okay? And what does that mean? Well, what that means is we're going to take the lead derivative along delta x mu, right? So you think of that as a vector field. Basically, you declare that it's delta lambda times some vector field. So you're basically doing this variation along the integral curves of some vector field. That's kind of the idea, but with an infinitesimal coefficient delta lambda. Okay, and now see delta x mu, which is the variation of the boundary, happens in directions that are normal to the boundary and happens in directions that are tangential, right? And basically, if we then break up the variation when written in terms of this Lie derivative into these two component forms, then you get this rather unwieldy looking expression, right? So this is Cartan's magic formula plus basically this decomposition. Okay, so here we're going to use some identities. Basically, the fact that this interior derivative is also nilpotent, like the exterior derivative, and that you have some sort of simplifications of what it means to take the interior derivative with the coefficients, that the coefficients come out front. And sort of parsing through it all, in the end, you get the following. So you get the Lie derivative along delta B, where delta B is a sort of tangential part of the variation, plus delta A times the Lie derivative with respect to the normal of in omega. Okay, and we know what this is, right? This is just K times d sigma, right? This is d sigma, and this is going to give us K times d sigma as we showed above. This, on the other hand, will give you the divergence sort of along the sort of tangential divergence along the hypersurface of delta Bi. Okay, so this is the total formula that we get. Great. So then basically what they say is that if you just looked at the area, by which they really mean the hypersurface volume, and consider its variation, then you get these two terms. And for certain choices of what these variations are, you get some interesting results. So first, if you have some junction, so if there's a junction of this boundary, this hypersurface with something else, or if you actually have a boundary of a boundary, then you get to use Stokes' theorem and you get the following structure. And they also show what that expands into. But notice that if you have basically no boundary of the boundary and you take delta A to essentially be 1, right? Which means that the dot product of the normal, right, with delta x is basically 1. So V is along the normal direction. Then this variation gives us essentially something that looks like the Gibbons-Hawking term. So the Gibbons-Hawking boundary term is itself a variation of the area. And then there's a more sort of formidable exercise of working out the second variation of the area formula, which will really matter in the derivation that follows. But the second variation gives us information of much more than just the extrinsic curvature, right? Because it's going to involve the Lie derivative along the normal direction of k, right? So that's like the Einstein equations of motion, if you thought about it. Well, I mean, it's just also, you can use the Gauss-Kodassi relation to work out what this is. But this is how you get information basically about the, get information basically about the Hamiltonian, the gravitational Hamiltonian. So that comes from the second variation of the area. So they basically use that in clever ways. Okay, so let's go back to the body of the paper and see what they do, right? Okay, so they say that really you have the Einstein-Hilbert term and you have the Gibbons-Hawking term. So begin by varying the Einstein-Hilbert term, right? And everything is standard up to the fact that you actually are going to do this variation of the embedding on the boundary, right? So that's carrying with it R, right? This is the covariant R. It's a bit confusing, but it's being integrated over the boundary. And then here we have essentially the equivalent of the type of expression we had in field theory, where we had something like the momentum, the sort of Pauli momentum times dq, but you see, because of the peculiarities of the Einstein-Hilbert action, you have the variation of the Christoffel symbol here instead. So having this on the boundary and actually just wanting to just vary the metric and not the derivative of the metric is what necessitates the addition of the boundary term to begin with. But anyway, they say let's carry on and rewrite that term in terms of the extrinsic curvature. And in so doing, you get the following final answer. So this is the boundary variation of the Einstein-Hilbert action. In the bulk, we just have the Einstein tensor as we normally expect. And so holding the boundaries fixed, meaning delta x is 0 and delta g is 0, you have the following reduction. You have delta trace k times square root gamma, right? So this is just the standard story where you just recover the Einstein, get the Einstein equations in the bulk, provided you add something to cancel this term that's being added. That addition is a GHY boundary term. And so here they sort of go back and use the fact that actually the Weiss variation of the Gibbons-Hawking term is really like the second variation of this area function. And what they find is that actually that's going to yield the following term, right? So it's going to yield the following combination. And this, again, should look familiar. If you've seen anything to do with, anything to do with the gravitational Hamiltonian, this is a familiar expression. I'll just leave it at that. And then they also take into account what happens if you have corner. Okay, so now the full variation of Gibbons-Hawking involves the regular variation with respect to the metric and the variation with respect to the embedding x, right? So there's delta x related terms here, which is important because this is what reveals the Hamiltonian. And then there's the metric variation terms here, right? This is the stuff that cancels against the variation of the bulk, right? Provided we fix delta, so if this is 0, right? That term, that means that we're fixing Dirichlet boundary conditions. And all that needs to be canceled is delta k, and delta k is canceled by the variation of the bulk term. And indeed, that is what we see here. So when we add everything together, then purely on the boundary, we have the following structure, right? So here we've not committed to any boundary conditions, but if we did commit to Dirichlet, this would vanish. But in addition to that, we have the following addition, right? We have the following term. And what they say is, okay, what we want to do is introduce now the delta, big delta variation of the metric, right? So remember, we did this at every step with this Weiss variation. We're not writing everything in terms of the regular delta, little delta variation, but we want to write it in terms of the big delta variation, not of the embedding field, but of the fundamental field at gamma here. Okay, so now it's a bit more complicated than what we had before, right? So we're going to take the lead derivative with respect to delta x of gamma mu naught. That's the analog of the, just the covariant derivative like we had in the field theory case, the generic field theory case, and then the time derivative like we had in the mechanics case. And again, delta x has the decomposition it does into normal and tangential pieces. And expanding that out, you see that we get the following expansion, which involves the lead derivative of gamma with respect to n, this combination of acceleration terms, and the lead derivative with respect to b of gamma. Okay. And then we sort of invert that relation and plug it back in, right? So it goes in multiple places. It goes in the variation that we haven't set to 0 yet, right? Because we haven't fixed boundary conditions. And it also goes into the second variation that we have over here. So basically, we see that we get, okay, when the dust settles, in addition to this term, we also get the following. So we had one delta gamma here, now it goes and becomes big delta gamma. So we have this symbol instead. And in addition to that symbol, we get the following, right? We get this lead derivative term, gamma ij. This should look familiar because what we have here is we're collecting something proportional to the canonical momentum. Canonical momentum, lead derivative with respect to some vector field, gamma should remind you of the momentum constraint, which is exactly what it is, right? That's exactly what it simplifies to when you actually go and do the calculation. But if you have a corner, then that term is also responsible for giving you the Brown-York type energy density quantities. So it's the energy momentum quantities basically come from the intersection of the boundary, say with a Cauchy surface, and they will basically know, or you basically have the energy momentum coming out as a result of integrating this term by parts, or using Stokes' theorem. Okay, and now see that if we take again the variation of this boundary embedding delta x to be proportional to n, right? So if you do a normal variation of the boundary, then we recover the Hamiltonian, right? So you see that that's exactly what we get here. We have a term proportional to n mu, which is the Hamiltonian constraint, and then we have the momentum constraint. But really, you can wrap them together into what they call the canonical energy momentum tensor for the gravitational field. What's nice about this is that it doesn't commit you to be doing this variation. It doesn't say that the normal has to be time-like or space-like. It just says that you have a normal variation, and based on what direction you do it, you have the following sort of canonical energy momentum tensor, which then combines with what you get from the matter, right? So this is briefly telling us, okay, and the sign epsilon knows about whether n is going to be space-like or time-like, but basically this is telling us in sort of compact way what we know both from the ADM analysis, giving us the usual Hamiltonian, that is that the Hamiltonian constraint knows about the deformations of the Cauchy surface normal to itself in the time direction. And also what we know from holographic normalization, which is that there's a radial Hamiltonian constraint that tells us what happens when we move the boundary along the normal to itself. They even comment on this. So they talk about the Hamilton-Jacobi formulation, and here they take this normal to be the normal to some boundary, right? They don't even really specify. And exactly as we've seen in sort of other discussions on this channel, you get this gauge fixed Hamiltonian density, which is exactly what features in the gravitational Hamilton-Jacobi equations. So that's yeah, I thought that was a very neat way of getting everything to come out. Basically, from knowing how, in addition to varying the fields, you also vary the boundary, right? So where is that? Yeah, basically, you have the terms here that know about this delta x. So they also go on to show how you actually recover the Brown-York quantities, what happens when you're doing the Weiss variation when there's both space-like and time-like boundaries, and you get the quasi-local energies and so forth. And these authors do have other references where they talk about similar issues. But what I wanted to comment on was that this reminds me very much of some other sorts of tricks in the literature, specifically around edge modes. So there's a whole literature around edge modes in gauge theories and gravitational theories. And there was always the obvious case that I thought was missing, which is, well, what are the edge modes associated with pushing the boundary in a normal direction, you know, like in a gravitational case? And that just had to be the Hamiltonian. So there's this weird sense in which the Hamiltonian always knows about the edge modes associated with moving the boundary normal to itself, either the radial or the sort of standard Hamiltonian. And it's very nice to see that there's this little neat trick that encapsulates that idea. I also thought that it was very interesting how they managed to get the area, or what they call the area variations, to be related to like the Gibbons Hawking term and other such things. That might be something of a clue. And it might also connect to stuff like the sort of entropic discussions of, you know, like getting Einstein's equations out of entropic considerations, you know, thinking Jacobson and so forth. So I'm sure that if I talk to people that are versed in that literature, they would not find any of this very surprising. I just thought it was very neat. So yep, another short episode. Yeah, I'm sorry I'm infrequent with this. It's become less theoretically podcasting and more occasionally podcasting, but hopefully I will re-stabilize and have some guests on. Thank you for getting this far. If you like this, please leave a comment, like, share, subscribe, and I'll catch you later.